1 minus TL over TH. This 0.4 equals to 1 minus, what is TL? 290 over TH. So this is the first scenario. If I'm using math now, I can carry him to this other side, right? To make it easier, I can carry 1 to this other side. Look now, you can carry 1 here. Can we see? So that is 0.4 minus 1 equals to minus 290 over TH. If you do that, what does this give you? Minus 0.6 equals to minus 290 over TH. So if I cancel, what's my answer? 0.6 TH equals to 290. That means your TH is what? 483.3 Kelvin. So this is your guy. Now that's not the question. The next one. Now told us how much should I increase the temperature of the hot one for me to have a new E of 20. So I would like to do this again, but this time around I'm doing it with the E of 20 in mind. Don't know if you are following me. So 50 over 100. 50 over 100 is what? 0.5 equals to 1 minus 290 over TH. Are we together? Now from if I carry 1 here to become minus 0.5, I hope we are together. Equals to minus 290 over TH. If you cancel your minus, what does that become? 0.5 times TH equals to 290. So that means TH will now be what? 290 over, what's the answer, please? 580 Kelvin. So what was the question? How much does the temperature of the higher have to be increased? Your answer will now be 580 minus 480. Any answer you have is correct. Any answer you have is correct. So that is that for that. So she will help me send this to the group. A lot of questions here they can try. Is it on this topic? No, this is another topic. It's hydrodynamics. When is your test? We can stop. Very good. Any question, please? Please check if anybody from online have questions. I answer and go. You have question? Ask. Where's the what? 50 over 100, please. 50%. It was made in the question. They said in the question, a Carnot engine whose lower energy reservoir is 10 degrees Celsius has efficiency of 40. So that's a scenario on its own. And find the higher energy. And the higher temperature is 483. But now the number on that scenario, how much should the temperature of the higher one increase for me to have a beta efficiency of 50%? So in the question, they are giving out the second efficiency. That means they are just creating another scenario. Tell us what would have happened for me to have efficiency of 50%. So what I'm to do is to also find what the higher energy would have been, higher temperature would have been, and then I subtract and I have the difference. Though of course there are ways to do this mathematically without even finding the heat, the temperature. Any question? Any other question? Any other question? No question, I believe you. Ask now, sir, something there in your mind, ask it. Check online if there's anybody that has questions, so I can answer them. So you have understood all I've said. Alright, so in summary, let's start. What have we said? Thermodynamics, listen. Thermodynamics is a type of, or is a branch of physics that studies relationship between heat and other forms of energy. Are we together? Heat and other forms of energy. Heat, that's in clay terms, heat, work, temperature, which is not even a form of energy, but it plays a important role. And then the energy changes. Now what do we now say that we have a system and a surrounding. System can be closed, open, or isolated. Classically, in what we are learning, which one do we tend to have more? Closed. Now we now want to say, and in that closed, matter does not change. What changes? Energy. The form of energy can be changing. We now want to now talk about the fact that, okay, we have three major parameters: work, internal energy, heat, and work. What did we say about heat? form of energy that can be transferred, hotter to cooler. There has to always be a difference in what? Temperature. We also said that he has other things we said. Is that Q is in joules. Now, number 2, we talked about internal energy, which is the sum of kinetic and what? Potential energy. And we also said that for that particular guy, he's dependent on whom? But it is independent of whom? So that is that for that. Number 3, we made mention of work. We say work can either be done by a system or done on. If it is by a system, what is that? If it is on a system, what is that? If it is expansion, is the work done positive or negative? If it is compression, is it positive or negative? So that will affect our formula. Now, the next thing we now went on to talk about was now the equations of thermodynamics. Please look for the third law. Third law of it. When we talked about the heat, we talked about zeroth law, which I know that we all know by now. That the implication of zeroth law is that everybody that is in thermal equilibrium have what? The same temperature. And we now went ahead to say that for my thermodynamical laws first, the first one is energy conservation. That the heat I bring into a system will either be used to increase the internal energy of that system or to use for work. Or in some scenarios, it can come in only for internal energy. That's one. In some scenarios, it can come in only for work. In other scenarios, it can come in for both. Are we together? Now, that formula was now given that change in Q equals to what? In U plus change in W. Now, we now try to say some things. Number 1, for my change in Q. For the first thing we said, for my change in Q, what do we note about my change in Q, please? Oh, we said there were different processes. Let me put it that way. The process, what are the thermodynamical processes? Isothermal, what is key about him? Constant temperature. So what will happen to the formula? It's lost. So the other incination, any heat coming into the system, what heat for the system? Any heat coming into the system will be used for work. Number 2, what else do we say again? Isochloric, volume. So who will volume affect? Work. So if it affects work, what will be the effect? Any heat coming in will be for what? Internal energy. I hope you understand. Because there is no work. Are we together? Number 3 is adiabatic. No heat is coming, no heat is leaving. So what will be the effect on the formula? Expense of internal energy. So anytime you have to deal with adiabatic, while work is being done, internal energy has to drop. So temperature will also do what? Drop. Now we went ahead to do some calculations with it, which I know you are conversant with it. We now came into, after calculation, we talked about second law, which talks about efficiency of a machine. And we said no machine can ever have an efficiency of what? 100%. There must always be something wrong. It must lose heat one way or another to the surrounding. So it is not so perfect. I can supply heat to a machine, but that heat will be lost along the way. I don't even understand. So the heat, your electrical energy that comes into the fridge, is not all of that electrical energy that is used to do the work. Some of it is lost. And that lost energy, or that lost heat, is what will make that area behind the back hot. Do you understand? It's not everything you use. So we now talked about thermodynamical cycles, which is really in machines. And we have Carnot, we have what? Otto. Carnot is like the ideal cycle, and it is reversible. Having isothermal expansion, adiabatic expansion, isothermal, adiabatic compression. I told you to look at where it can be found, but the classical place that uses the reverse Carnot is a refrigerator. Now for Otto, you have the same pattern. Start with isothermal expansion, but there is no expansion in this other place. Instead, it's just an isochoric process. That's where you have same volume, nothing is expanding or decreasing. Then you now have compression, which is still isothermal. Then you now have an isochoric. So that was that. Then after that, we now try to look at efficiency. The formula. We have the formula of efficiency for machines classically being work output over input times 100. But if you ask for performance, especially for Carnot engines, there's a special formula for them, 1 minus temperature of cold over temperature of what? Hot. So you just see that in that question, all they will give you, that they'll give you temperature, cold and hot, ask you for efficiency. Or give you efficiency and give you one of the temperatures and ask you for the other one. Is that okay? You just use the formula and go home. Now, beyond that, if for any reason any other thing can be brought, I trust the Lord that you'll be able to solve it. In the name of Jesus. Thank you very much for your time. I appreciate it. Okay, here's a question. Eh? What was the formula? Q1 minus Q2 over. Please let me see the notes. Hmm? Let me see, please.
Same question here. And W equals to change, and W equals to minus P change V. Any formula B is to calculate what goes by reaction. Chemical carried out in an open vessel. And this second one too. W equals to minus F times can be used to calculate what goes by the system. Expanding equal to force of gravity.
Okay, concerning work done, this is the idea. Concerning work done, like I said earlier, work done, physics classically is always work done by. Whatever doing chemistry is work done on. But even though it is asked and it is in physics questions that you saw it, whenever they say by, that is the only time you have to use P change in V. When they say work done on, you have to use minus P. So the minus is only used when there is what? When work is done on the system. But if it is work done by system, what do you use? Plus. So that's just the idea. It's just really for the formula pattern. Nothing else it can help you do. Then for the other one, which is asked of force time distance, there's no way you can use that formula. Someone asked the question force time distance. There's no way you can use the formula force time distance because you will not be given in these questions. It's not like when I taught you about what did I even teach you? Hydrodynamics. In hydrodynamics, there's no mention of force. Like pressure will now be brought in, volume will be brought in, speed will be brought in, but nobody will be bringing in force there. Similarly here, you not write a question and it is a question on thermodynamics and they're asking you force. They will bring in pressure, they'll bring in other parameters. Do you understand? But even though force was brought in, change the force to pressure. But there's no need for things. So that is just that for that. You're asking a question. Yeah, I want to see the notes. There's someone that has notes now. Where is it now? Sir? Where? Say performance is inverse of efficiency. I'll check it and get back to you, please. Let me pause it. Let's stop it. I'll check it and get back to you. I'll send it for you. Thank you very much for your time. Hope we can stop here. No other question, right? Problem. Put a metal in the fridge. Cold. Now heat transfer. Where does heat transfer always move from? Where does it go from? Always from hotter to cooler. So if I bring out that thing, who is hot? That was outside. It means that the one that was outside is transferring heat to the one that you brought out of the fridge. It's the same pattern of bringing out cold water from the fridge. When you drop it outside, the surrounding is hotter than the fridge. So that surrounding will just apply heat to the fridge. So it's giving heat to the container. And when it gives it to the container, the water itself gains heat and becomes this thing. Yeah. That's just the pattern. Thank you very much for your time. We can stop. Please, they should stop the video. Sir? Sir, you can stop the video now. Someone has question. Oh, Jesus.